Okay, good. So welcome to the ECSESS Professors Speaker Series, the September 2020 conference on photonics and computing. It's great because we will see the interplay between these two fields. Professor Odile Liboiron-Ladouceur, who is working in photonics that has many applications to computing, and Professor Dubac, who is working on compilers, which are one of the, well, a backbone for computers and computing in general. So of course, well, we would like to greet you with coffee, with the traditional coffee and croissant, but it won't be possible this year, unfortunately. But I mean, there are other upsides, right? That we can reach more people since it's online. So this is the main downside for me. So about the speaker series, so it's really an opportunity to broaden research horizons of students at McGill, and in particular in ECSE. Also to see the interfaces between ECSE research, so research in electrical, computer and software engineering, research with other fields like mathematics, physics, computer science, health and medicine. Learn about the new directions and research on new technologies. And special to this year, we will have 2 conferences per semester. So save the date for November 10th. So a little bit more than 1 month. So our first speaker is Prof. Odile Liboiron-Ladouceur, who is an associate professor in electrical and computer engineering at McGill, and also the Canada Research Chair in Photonic Interconnects. So we'll just give a short introduction. So Prof. Liboiron-Ladouceur holds a Chair 2 Canada Research Chair in Photonic Interconnects and is an internationally recognized experimentalist developing proof of concept prototypes of novel integrating photonic devices and subsystems for data communication. She has 44 peer-reviewed journal papers and over 90 peer-reviewed papers and conference proceedings. Prior to joining McGill University in 2008, she was an intern at IBM T.D. Watson Research Center in 2006, where she participated in DARPA-funded projects on off-chip photonic interconnects before completing her graduate studies at Columbia University in New York City. She worked in the industry as a test engineer for prestigious firms like Texas Instruments, Texas Instruments in Texas, of course, and as an application engineer for Teradyne in Boston, Massachusetts. She is also a proud graduate of ECE in 1999. So la parole est à vous.
Merci. Thank you very much. That's great. I include a short bio of myself, but you did a better summary than I did. Let me just figure out my slides here. Okay. All right. We see my screen. Okay. So I picked the most hot topic title I could find, and I'll talk to you about photonics and how we can use it for AI, and then how AI is influencing photonics. All right. Okay. Well, I'll start with a bio. Ken, thank you very much for the intro. That helps me. I decided to do this slide just because as an undergrad, I wish I knew a bit more about the professors, because I find them so intimidating that I didn't have the courage to ask them about what they do in life and how their research. So this is a slide to maybe make myself more familiar to you, and really if you want to reach out for questions or anything. But I'm also very local. I won't say when I'm born, but you can figure it out. And I have 2 family names because they come from both my mom and my dad. I have my favorite pictures there. My dad is a physician and my mom was in occupational health. And I was inside there. And so I grew up in NDG, mainly. My parents were pretty divorced, that's fine. I had 2 birthdays, 2 houses. It was not bad for me. And I grew up after in Saint-Albert. So I went to Sainte-Catherine-de-Sienne in NDG for my elementary school. And then in Saint-Albert, I graduated from Collège du Rocher, like Ken's, I found out. But in my days, there were no men. It was just women. And then I went to Cégep Bois-de-Boulogne on the other side of the island, Why? I was mainly into sports and somehow got recruited by the basketball team there, which was the worst in the league, but who cares? I felt it was a good CJEP. And I'm not that tall, and I didn't go further. I never played at university level except intramural. And then I went to McGill. There's no engineers in my family. It was just because that's how I was. I would disassemble every Christmas gift I would get, from a remote control car to a TV at the cottage, and almost electrocuted myself. But that's what I like to do. So then I went to, so in '99, it was the boom in telecom. And I went to the US. I wanted to be on my own. My family is very close knitted, and it was too much for me. And the salaries were also better in the US, so I decided to go there. That's where I learned English, because when I did my EE at McGill, I recorded every single classes. I had headaches every day in the first 3 months. My English was very poor at the time. So I came back from the US saying Z for the variable Z, and I got schooled by many undergrad students when I started teaching. But in the US, it was fun. I lived in Boston, and then in Texas, Dallas. As weird as it can sound, I really love Dallas. It was a fun place to be. Then there was an economical downturn, and I decided to go back to school. And I went to Columbia University, which is in New York City. That was really a nice place to be. It took me forever to do my PhD for that reason, but it was a great experience, and I miss it tremendously. And then I was flip-flopping between industry and academia, and made my decision. And then since then, you know, I got many kids. I have a large family, and that's us today. This is me in the lab in those days. Let me use my pointer. All right. So that's my group today. I have a relatively large group. It happened this way. I like it this way. They feed each other. They work together. As a former captain of basketball teams, I like the team aspect of research. And so, but I have to say now I have too many students because some were supposed to graduate earlier, but with the pandemic, so there's kind of a bit of a lag, but the new students arrive and so on. But my students after this, their graduate studies, they end up mainly either in Canada or in the US, a few in academia, many in companies, some in startups, some in industrial lab, important industrial labs, but a bit everywhere. All right, so this is where I come from. With my industry experience, it was very much hardware. I was an application engineer for test instruments, to test chips, to test electronics chips integrated. And when I went to Texas Instruments, I became a test engineer for their chips. So you had, when the design was done and fabricated, you had to develop an automatic program that would check if the chip works, and then you have to ensure high yields and so on. And then we started doing associated electronics for optical systems, and that's how I got exposed to optical systems. And I'm very much of a system hardware development. And so when I started my academic position at McGill, amazing things happened, and it was really exciting. So my PhD work is on the left. It's an optical switch. The idea is to connect servers using optical fiber. And this allowed for tremendous bandwidth, high capacity. So at the time, our projects were funded by DARPA, NSA for like high performing computing, all sort of things. There was no AI. It was just like crypto analysis and crazy things. Weather forecasts. I mean, it's still required, it's still needed. So you need high power, high processing power, and interconnectivity between servers because they work in parallel. So we developed this 12 by 12 kind of switch that would connect 12 computers with fiber. It's a big mess on a big table. And now what happened, and I'll show a bit why this happened, is we can integrate those optical functions like modulating a laser or detecting photons or manipulating photons. Before they were big components. Now they're all integrated on a chip. So quickly after I started my academic career with my student, this kind of system you see on the left, within 10 years, it was on a single small chip. And this is where I stand. And for me, it's like, oh my God, that means all those systems, those crazy systems that people have been thinking for decades, now we can make them more practical, where we can put them on a small chip and integrate it, embed them in another system. So it was a big, big step. So on the commercial side of it, that is changing a lot. This is why the internet is so powerful. We can process data a lot better. The processors alone are getting faster. They have like billions of transistors. The challenge before was to bring that information outside the chip, and it takes a lot of energy. But once you convert it to photons, now you can use optical fiber with very low loss. And so with integrating optical functions, what allowed people to do is to bring that conversion from electronics to photonics much closer to the processor, so that you eliminate all the energy you need to push the data from a processor to the optical transceivers, which would convert to optics. So you can see here, it's a cartoon showing that the OE or the EO, the electronics to optics or optics to electronics, is getting closer to the processor. So that's from a commercial point of view. And around 2007, there's been like a few papers on using CMOS technology to now integrate those optical functions. That was not possible before. I mean, there were papers about it, but it's very like research. But suddenly it became commercially viable. And so in 2010, starting 2010, a lot of places in the world decided to invest tons of money in making sure they have the fabrication center to develop those chips. So Asia, Europe, North America, and I put here Obama, we miss Obama, announcing a big, big investment in AIM, American Institute of Manufacturing, which is in New York State. And they can make integrated photonics. So what does it look like? What can it do? I mean, I'll talk a bit what it can do. What it looks like, it's basically like a chip, like maybe you've seen before. It's integrated, it's small, it's 1 centimeter by 1 centimeter max, and you have hundreds of functions. And so I put examples here. So they refer this to silicon photonics. There's different technology, but the one that is generating a lot of attention is referred, or it's based on a silicon on insulator, the silicon being the semiconductor. And the reason why people are going nuts about this technology is because it's leveraging the CMOS technology. So since the 60s, there have been billions of dollars invested in fabrication centers that can make the chip you have in your cell phone that has like billions of transistors. It's cheap now. There was a lot of investment. So with silicon photonics, we can leverage that equipment and also implement optical functions on it. So I won't make this too much related to theory, but the idea is to confine the optical signal inside a guide, a wave guide, and with total internal reflection. So it's the same thing that you've learned maybe in physics, where light will bounce within a core area that has an index of refraction higher than the surrounding, and that's Snell's law. And so it bounces, and so it's the same idea that you have, but it's a rectangular waveguide because it's easier to fabricate it. And so now with those precise fabrication facilities, we can have multiple, how will I say, they're like Lego blocks. So now I can have one block that can guide the light. I can have a optical to electrical converter. That's another piece of my Legos. I can have a modulator that shuts the light on and off. So I can put all those pieces of Lego together and build a system. And this is what basically I do. So in that context, photonics for AI. So now you understand, hopefully, that in the last 10 years, there's been tremendous change in optical systems because now we can put them on chip. Now that we can put them on chip, how about we develop photonic accelerators for AI? And this is the hot topic. And as I speak to you now, I feel I'm missing new papers. It's very active. And I was just searching for images for this presentation. I'm like, oh my God, I didn't read this paper. Oh, I should send this paper to my student because a lot of activities. So the idea is that, and I'm not an AI expert, I should say, so I'm learning through my students. That's a beauty of doing academic research is you have students that eventually know more than you do and they teach you, and that's part of the training. So the idea is to replace some of the hardware, electronic hardware, that represents the layer between those neural networks that can do the math or can do the functions between those, okay? And I would say in the last 5 years at MIT, there was this famous paper that everybody is referring. Out of that group, there have been 2 startups, Light Matter and Light Intelligence, that started. There's some in France, but on this idea of developing chips that would be used as accelerators, and I have a picture here. And there's a famous conference, Hot Chips, that is not necessarily photonics, it's more like high computing hardware. And they introduced, I think this was Light Matter that introduced the Mars Photonics core, and having a photonic matrix. And the idea here is to use photons to do matrix manipulation so that you can do the computation required in a neural network, for example. And I'm actually involved in one, it's a collaboration, and I have an intern there. Optical is a startup that started from Tendon Launch. Maybe you're familiar with that organization. It's kind of a, how do they call those? It's like a place where you can start companies. And so now they branch off, they got the funding, now they're on their own, called Optical. So they're testing new ideas on that front. And the building block, the essential block here is it's an interferometer. And that's a really old device, basically, where you take your optical signal, you split it in 2, and then you bring it back together. And depending on the phase difference, because if you recall from your physics, optics is it's an electromagnetic wave with amplitude, phase, frequency, and so on. So if you play with the phase, if you can change the phase slightly, you can play with this concept of constructive and destructive interference to decide how much light will come at the output port. So you can see here how if you can just change the phase a little bit, and it turns out we can do that precisely, you can decide how much your weight of your light will come out. So based on that building block, I have a couple of students that work on this, and recently Farad just defended his work 2 weeks ago on using this Mach-Zehnder interferometer, playing with the phase, and basically that represents a matrix, and you can do a linear transformation of the input vector. And I'm not going to go over this because I would have to study it again. But we have a paper about this if this is something that triggers you. But the message here is we can do matrix computation. And if you put together many Mach-Zehders in a very specific topology, you can scale your matrix to multiple items, multiple array. And so that's the idea behind actually light matter, light intelligence. That's what they're doing. They're using a structure like this. Of course, there's a lot of the hardware development that needs to happen because you need to control the phase and so on. But this is what's behind this. So we've been doing a lot of work because, of course, it doesn't scale very well as electronics. We can only do up to 32 by 32 kind of matrix. So we do a lot of analysis to figure out how to improve this. So that's photonics for AI in a snapshot. It's very hard to go and dig in, but I just want to pick your curiosity, and there's papers here, and I can give you more information, where to find more information about this. So now AI for photonics. Okay, what's going on? I'm kind of flipping the two words, and it's not a typo. AI is also beneficial for photonics. So now we're going to do some physics. No, I'm just kidding. I just want to remind people of photonics integration. Basically, we're working with electromagnetic wave. You'll notice here I grab slides directly from my course that I'm actually teaching next winter, if that is of interest. And in this field, you kind of have to be able to digest Maxwell's equation a couple of times. But we have numerical tools to help us. Basically, we need to use Maxwell's equation to figure out how is the optical signal going to travel within a boundary defined, right? So at first it could be like, oh my God, too much math, but it's not something we use every day. Once we understand how light propagates, once you understand those basic concepts, then you get into building your system. So silicon photonics, again, we have to design the waveguide in a precise way, controlling the index of refraction, and you can manipulate the light very well. So here is, again, coming out of my course, is a splitter. So you can kind of play with interference in having a light going into a structure that is open that will kind of split into 4. So you can have 1 by 4 or 1 by 16, but you'll have 1/16 the amount of photons. So you have to keep that in mind. But these devices, okay, there's a theory, and then you need to simulate them. We have tools for that. And they're kind of tedious because it's only with experience that you realize what works, what doesn't work for fabrication. So where's AI in this? Well, maybe 5 years ago, they started to investigate how some AI-based, AI-related algorithms can help us design. So instead of using our intuition, human intuition, now we're kind of using algorithm to define the performance we want, and just let the algorithm design the structure. And you get, so on the bottom left here, you have a 1/2 splitter, and the splitter is such that light at certain wavelength will go to the top port, and the light at other wavelength will go to the bottom port. And in a conventional human approach, you would have like this open structure, and you would play with the dimension, put the ports, the input-output ports at the right spot. But if you let the algorithm figure it out itself to improve like the maximum power, crosstalk loss, you get those funky structure where you have like black is where you have the silicon, and white is where there's no structure. So somehow this structure, which is referred as inverse design, is actually offering high performance. So this is very new to us. I would say it's the last 6 months to 1 year, and we're submitting a paper. I have to review it. It's almost ready soon. And so now suddenly we have AI algorithm that allows us to do a lot more in photonic integration. So imagine already in 10 years, we've accomplished so much. Now we can improve those performance using inverse design, or using algorithm that assists us in the design. And you end up with those structure every time. I'm like, it's like I'm going to see a psychologist. What do you see in this image? You know, it's just weird. You wouldn't really think about trying this on your own, right? So, but it works fantastically well, better than what humans would do. So we can get rid of humans and students and let AI take over the world now. I'm just joking, of course. You need humans to bound all this, but it's quite amazing. I'm impressed, and I'm learning so much through my students about this opportunity. So that's AI for photonics, and that's it. I didn't want to talk too much. So I hope this kind of gives you a snapshot. It was very short, but if I went too deep, maybe it would bore you. But I am teaching 2 courses this winter in photonics, one of which is you can take, it's 430, it's cross-listed with 540. You should have taken electromagnetic wave to be able to navigate this course without too much of a headache. I also teach a graduate level course, 596, where we're actually designing a Mach-Zehnder interferometer and see how it works. But also I want to point out to you guys that now that conferences are virtual, one nice aspect of this is they are often free. Usually they're $500 and you have to travel and so on, but now everything is online. So you still have, if you still have brain power, I know you guys are busy, but if you want to learn more about research topics, actually we have 7 papers to that conference and I'll post it on LinkedIn. That's also something else. With Facebook, I'm not friends with students, but with LinkedIn, I'm happy to be contact or whatever you call LinkedIn friends. And you can see what I post. Usually I post events. We also have a photonic networking event that will be virtual, where graduate students from Montreal are presenting their research in photonics. So that could be very interesting for you to figure out, because it's not just McGill. I mean, I should say McGill is the best, but there's also Polytechnique, INRS, Concordia, UQAM. There's a lot of universities in Montreal doing research in photonics. So you can get a snapshot of what's happening. And my website, personal website, is the worst ever. So if you want to see the latest about our work, Google Scholar is a good place to look at. And I'm trying to be more social network savvy, and I post some events on our LinkedIn, well, on my account. So feel free to check it out. So that's it. Hopefully it was okay, but I'm happy to answer questions, not too technical, or anything you have on your mind. Curious.
We are on time, probably, Liboiron-Ladouceur. Thank you very much. It was a very interesting talk about photonics and to see the interplay with computers and high performance computing and no AI. So is there any question? So you can raise your hand for Prof. Liboiron-Ladouceur. Or you can demute yourself.
Oh yeah, we can do chat if people are shy. But
yes, or you can chat is fine too.
Yes.
I can ask a question.
Yes, thank you.
I don't know if it's really or how much time it's going to take. For the AI and photonics part, I was wondering if there's anything special about the photonics aspect of it, or is it just the electromagnetic simulation? So for example, I know there's like computational electromagnetics at McGill. So what makes this part different from what is done in electromagnetic simulation?
So we do electromagnetic simulation regardless of using AI algorithm. The difference is that instead of like, you would play with the dimension, you would kind of, from the theory, figure out the dimension of your structure based on Maxwell's equation, okay? And once you have an idea of your dimension, you would kind of simulate this and use the numerical tools, kind of give you an idea of what you'll get at the output. And then you would go back and try something else. And there was a very manual way of optimizing your design. The difference with inverse design is that you would kind of partition your design space to allow the algorithm to decide should I have silicon here or your silicon dioxide, because the field will exist in the blue here. And this is the optimization, and this would be done through several iterations where the performance would be looked at, and it would be a loop. If the transmission of the light is not strong enough, it would do another try and change this. And the structure here will kind of morph automatically through that algorithm. You could do manually, but it'll take a month. But with our computing power now, you can do this, and if you develop the algorithm well, it could be quite quick. So in half an hour, it would play with the structure, and suddenly you get this, and the performance would be superior to the regular structure of a rectangular. So that's the idea. So it's integrated within your electromagnetic simulator.
See.
Yeah.
So what structure are we actually designing here?
So yeah, so the publication is a lot about demultiplexing multiple different wavelengths, because that's important. In optics, you have a lot of bandwidth capacity because you can allocate one laser wavelength for each data. You can have like 50 gigabit on each of those. But when you arrive at destination, you kind of have to select which channel you want to look at. So that operation is important. What we're doing here, and I kind of skipped that part, what happens with integration is within one waveguide, depending on its dimension, you can have more than one solution to Maxwell's equation. So you can use one laser, but still have multiple modes. That's what they're talking about. So each mode would have a different electromagnetic profile, right? That's the electric field, the strength. Red is high, blue is low. So depending on which mode, you have a different profile, and these are orthogonal. So you can also encode information on each of those separate modes, which is tremendous because you use one laser and you can encode more than one set of channel. So we went into that direction. It's a bit research, but I think there's great values here because I can use 4 lasers. Each of those lasers I can excite 4 different modes. So I have 16 channels, 16 times 100 gigabit per second. I modulate. So right away I have 1.6 terabit per second of information in that structure, you know. So that's the beauty of silicon photonics. I didn't go on about it because it would need a little bit more explanation, but it's quite fascinating what you can do.
Thank you.
I think I saw a question through the chat, but I can't see the chat anymore. Oh.
We may have time for one last question. So
Okay.
yes, we'll do one in the chat.
Okay. Will the slides be posted? Email me if you want the slides. I'll send you. Are you confident? Oh no, wait. Can you explain what are the challenges of using photonics in chips? Right. Many challenges. That's why we need you guys to figure it out. I had it here, very, very small. So in silicon photonics, it's an indirect band gap. So if you do your semiconductor, you cannot how to say, generate the photons from an electron. There's some material where they have a direct band gap, and if you properly manufacture this, you can build a laser. You can generate photons by providing electrons. Silicon photonics is indirect, so you don't have that. So you always have to have the laser outside. So it's like your battery, and you have to bring it into the chip. And the biggest challenge is, I didn't show it here, but the optical fiber, relative to the waveguide, it's a factor of, 50. The optical fiber is really big with respect to the waveguide. So somehow you have to bring fiber, light from a fiber with that core into a small waveguide. So there's a lot of loss. So you have to do this, you have to engineer a way. So we have like tapered, we have grating couplers, we have all sort of ways to do this. With some material also, it gets hot. And so with heat, your index changes, your functions will change a little bit. So these are some of the main challenges that we're struggling with. Yeah, and I think, yeah, so if you're interested in this, I suggest you take 430 if you didn't pick your course. We'll teach you about this a little bit more. All right. I think that's my time. Oh no, okay, another one. Okay, one last one. Oh, you said thank you. Welcome. All right. Well, thank you everyone for listening. I hope I taught you something.
Thank you very much, Prof. Liboiron-Ladouceur, for this very informative talk. And for students that are interested in learning more about photonics, you can contact Prof. Liboiron-Ladouceur either on LinkedIn or by email. And also take her course, or plan to take her course in your curriculum. So ECSESS 430 and ECSESS 496.
Yeah, thank you. Thank you, everyone.
Thank you. Okay. So now it's our next, is the turn of our next speaker. So it's Professor Christophe Dubac, who is an associate professor in electrical and computer engineering and cross-appointed with the School of Computer Science. Another example of the interdisciplinary research and engineering, and also a Canada CIFAR AI chair, CIFAR, the Canadian Institute for Advanced Research. So for the introduction, Christophe Dubac is an associate professor jointly appointed in the Department of Electrical and Computer Engineering and the School of Computer Science at McGill University. Prior to that, he was a reader, an associate professor equivalent at the University of Edinburgh in Scotland and the Institute for Computing Systems Architecture. He received a PhD in informatics from the University of Edinburgh in 2009, and he holds a master's degree in computer science from the Swiss Federal Institute of Technology, Lausanne. He spent 1 year as a visiting researcher at the IBM Watson Research Center, working on the liquid metal project. So his current interests include data parallel language design and implementation, high-level code generation and optimization for parallel hardware, architectural design space exploration, and the use of machine learning techniques applied to all these topics. So, Prof. Dubac.
Yeah, okay, thank you for the introduction. So let me share my screen, the first challenge of the day. Okay, you should be able to see my slide, title slide. Yeah. Okay, great. And I hope that you can hear me. If that's not the case, please let me know in the chat window. So yeah, great. Thanks for the introduction. So in this talk, I will be talking about language design, compilation, and hardware synthesis for machine learning acceleration. And I'm just going to give you a glimpse of the of what's happening in my group, my research group. So let's move on to the next slide, which is my very, very short bio. And thanks again, Ken, for summarizing this. So I am originally from Switzerland, the native French speaker. I guess you could have heard that. You should have noticed that by now. I did my studies there, my undergrad and master degree. And then I went on to do a PhD at Edinburgh University in Scotland or the UK, depending on your political view on whether Scotland is its own country. Then I went on to do a postdoc at the same place. And I also spent 1 year as a visiting researcher at IBM T.J. Watson in New York. So I think Odile also spent some time there, and I can highly recommend this place. If you have a chance to do an internship there in the future, you should really do it. It's a great place, a lot of amazing people over there, amazing researchers at IBM. And New York itself is an amazing city to visit. And then I was a professor at Edinburgh University before joining McGill in 2020 of this year. And by the way, this picture here, that's the view of Edinburgh. It's usually a lovely city. What is great about this photo and Edinburgh in general is that you can always use it for the background because the sky is so dark, you can always highlight things at the top when you have some text you want to write there. Because that's usually a typical day in Edinburgh. Rain, snow, and sun all in one day. All right. So why looking at machine learning? Why looking at acceleration? So machine learning, my view from a system point of view, you're having some output samples, you're having some input samples, and you're trying to learn a function from your inputs to the outputs. And the name of the game is finding f. Now, to find f, that takes a lot of computation, and that usually involves a lot of matrix multiplication. And this is an example from 2012, one of the very first deep learning algorithm called AlexNet, which was used for image classification. And the program size has 62 million variables. So that function f somehow inside has 62 million parameters, and training the model means finding these values, which involves multiplication of matrices. Now, if you look at the time it took to train this model, it took 6 days on a dual GPU system. So for 6 full days, you have 2 GPUs working non-stop to be able to train AlexNet. If you were to compare that to the time it would take to train on a CPU, the CPU of the time, it would take about 120 days. So what we're seeing here is that because we had these accelerators, these graphic processor units, this has enabled the training of very advanced neural networks such as AlexNet. And just to keep things in mind, this is the training time for just one round of training. But obviously, when people started designing this neural network, they had to go through several rounds to figure out what works, what doesn't. So imagine when you have an idea, you need to wait 6 days to get the result. That's pretty long time. Okay, so nowadays we can do these things much faster because we're having better and better accelerators. Now, one thing to consider as well is that actually these accelerators, these graphic processor units, they were not designed to accelerate neural network originally they were designed for gamers, okay? So it's a kind of accident that actually machine learning people have been using GPU ever since, because we found out that GPUs were really well suited for this problem of learning a model. So now when you have accelerators, that means you're having diverse hardware, okay? And this diversity brings many challenges from a system point of view. One is the programmability. That means that for every devices that you have, you may have to use a different programming model, a different language to program it. Portability is also an issue. If you have to use different languages or write a program in a different style, it means it might only work on one of these machines, okay? Performance is also extremely hard to extract for a given hardware. And what's even more difficult is performance portability. That means if you're tuning an algorithm for, let's say, your NVIDIA GPU and you want to run it on your AMD GPU, that might perform very, very poorly. So let's have a look at, what are the challenges? And in terms of programming, this is a very simple one. If you're taking an NVIDIA GPU, for instance, what you may have in your desktop, and let's assume you want to do something very simple like summing the elements that you find in an array. If you're using C as your favorite language, the program might look somehow like what you see on the left-hand side. You have an accumulator variable, a for loop, and you're just adding numbers into the accumulator. Simple, straightforward. However, if you want to get the best performance on this machine, this GPU, you have to exploit parallelism, you have to exploit scratchpad memories that are on the chip, you have to deal with synchronization, memory access patterns, and so on and so forth. And that program on the right is exactly the same one as on the left. It's doing the sum of an array, but for this particular NVIDIA GPU. So there is a real need here for having what we call hardware agnostic programming models or programming languages that allows programmers to express their program in the simplest possible way and then let some smart tools actually produce the horrible code to extract the last bit of performance on your hardware. So this is what my group has been focusing on, and most of the work I'm presenting here is from my past life at Edinburgh University, because I just joined McGill in 2020. So this is mostly my research group that you see here on the staircase of our computer science building. And the project that we created is called LIFT. And the goal of LIFT is to achieve performance portability across lots of different hardware. So what is the LIFT approach? This is your kind of system stack. You're having applications at the top, you're having then your domain-specific libraries or languages to program, when you want to program in a certain domain of application. For instance, if you want to do linear algebra, you're going to be using libraries called GEM. If you're doing image processing, maybe you're going to be using OpenCV, neural network, you may use TensorFlow, and so on. So you're having these different domain-specific libraries or languages for each domain of application. And then the idea of the LIFT approach is to say, what if we could create a single data parallel language that you could use to implement all these libraries, okay? And then having a single compiler which has some clever techniques in there so that you can target many different types of hardware and programming model underneath. So if we look what's underneath the compiler, you're having what I call device-specific interfaces. So if you're programming a CPU, you may use C or OpenMP if it's a multi-core processor. If you program it up a GPU, it might be CUDA OpenCL, VHDL, or Verilog for FPGAs. And if it's the TPU, the tensor processor unit from Google, you may use something called Accelerate, which is a kind of assembly specialized for this architecture. So the goal center of everything here, the heavy lifting. Okay. So in terms of language design, what we want to do is we want to abstract away as much as possible and stay away as far as we can from the horrible low-level details of the machine. So what we're taking here is called functional programming. That's the style of abstraction that we've chosen here. And we're having building blocks such as map, zip, reduce, which might sound familiar if you have used functional programming before. If not, I will just explain map because that's a very simple one to look at. The semantic of a map is saying you're having an array or a collection of data and you have a function f, and what you want to do is produce a new collection of data where the elements, where you have applied a function f on every single element. So f would be, for instance, multiplied by 2. So you may want to multiply all the elements of a vector by 2 and get the resulting vector. And what you observe here is that these patterns, these primitives, they're focusing on what you want to achieve rather than how you want to achieve it. If you think of this map here, I'm not telling you whether it's going to be sequential, parallel, whether they're going to be using a for loop. If it's an assembly, am I going to be using a branch instruction or whatsoever? I just tell the compiler, I just want to map this function over every element. Okay. So how can we express interesting things with this type of abstraction? So let's look at matrix simplification. And I think Odile mentioned matrix simplification early on when she talked about photonics for AI, because matrix simplification is actually at the heart of many machine learning algorithms. You can resume training a machine learning model to doing a lot of matrix simplification. If you can do that fast, you're going to have a fast, you're going to be able to train your model very fast. So let's look at A times B equals C. How do you do it with this high level abstraction? Well, it will go something like that. You would say, take the matrix A as an input and then map for each row of matrix A. The little lambda here, this is coming from functional programming. Don't be scared with that. That just means for each. Okay, so read that as for each row of A. Then for each column of B, what do? I want to do a dot product. With the primitive that I have, a dot product is expressed as take two vectors and zip them together to create pairs of elements, then multiply pairwise the elements, and then reduce, that means sums all the elements together, and that gives you the dot product. So this is the high-level input we would like to use for our compiler, because there is nothing hardware specific there. It's very hardware agnostic, okay? It's very abstract. So the next question is, okay, now that we have that, how do we compile that to and optimize this to get optimal code for the target architecture that I'm looking at? So we're gonna start with this functional program here on the left, very abstract. And the idea is that we can turn that very simply into C code. All you do is every time you see a map, you might say, well, I'm gonna use a for loop. So I have two maps over here, I have two nested maps over there. When I see a reduction, I might say, well, a reduction, it's a for loop with an accumulation variable. It's like the summing of an array. So that's another for loop, and so on and so forth. So you're having a very one-to-one mapping between this abstraction here and the C code you could generate. And you could even imagine going back and forth between the two. So now what we want to do is a traditional C compiler. What it would do is basically look at the C code and then start to optimize that C code, realizing, oh, perhaps I can fuse some loops, perhaps I can do tiling to get better memory locality, cache locality. Maybe I can vectorize the code and exploit some very specific instruction in my instruction set. But that's actually very difficult to do in compilers, and it requires quite a lot of coding in the compiler itself. So instead, we want to take a different approach. What we want to do is use a system of rewrite rules. So the idea of rewrite rules is from this high-level abstraction, find equivalence between programs. So here is a simple one. We're going to just look at the map fusion rule here. It says if you're trying to map a function f, you produce a new vector, and then you want to map a function g on that vector, it is the same as mapping on the vector the composition of f and g. So let's say you want to multiply a vector by 2 and then add 4 to every element. You do not need to produce a temporary result in between. You can just fuse this operation into one simple function that does times 2 plus 4. So this is the idea of map fusion. And we have a few other of these rules. We have about maybe 20 or 30 in the compiler. So we express basically what the compiler is allowed to do when it sees expressions, how it can modify them and translate them. So now if we come back to this example, and I want to apply optimization, what we're going to be doing is operating on the left-hand side because it's easier to reason for the compiler. We're going to say, hey, I have an opportunity here. There's a map. I've learned that there is this rule. For instance, this rule is called a split join rule that I can apply. What about I apply it and I turn this bit here of the program into that new bit over there. And this program that is produced here is equivalent to the previous one. Why is it equivalent? Because each of these rewrite rules that I have shown you here, I can prove it on paper that they will always be correct. Okay, always. These are like equations in math. Okay. Now that I've done this exercise, I can go back to my code generator, and this time as the code generator now produce a new C code from this expression here. And the result, if you look on the right-hand side, will be that the outermost for loop has been tiled. What is loop tiling? It simply means I am breaking down a for loop into two other for loops. Why is that interesting to do? Well, because of locality. And I won't have the time to go into the detail, but if you're more interested, I highly recommend that you take a class on optimization for architecture. Okay. Now the idea is that we're going to be applying a chain of rewrite rules where we're starting from a top-level expression and we're applying rules, and the expression is going to get more complex and perhaps more optimal. And this creates a search space because at each point I have a choice. There may be many rules that I can apply. Okay. And now what we can do is we can take the compiler and we can start to explore randomly choices of rules, or perhaps semi-randomly some choices, and generate a lot of different variants of the same code. And then we run all these variants and see which one wins, which one is the fastest on the architecture that we concern. This process is completely automatic. Perhaps it takes 2 to 3 hours to generate the best version, but given that the target here are these libraries, perhaps the machine learning libraries or dense linear algebra libraries, you only need to do the job once for each architecture. So it's okay if it takes 2 hours of automated time. So now, does this approach work? The short answer is yes, and that's to give you an idea of the type of application we have looked at. So we have looked at neural networks, machine learning, but also other things like coming from the physics. So this is an application that is called room acoustic simulation, and this is the problem of you want to simulate how the sound propagates in a room. So this is a dome room with some benches that have been modeled in the middle here, and the idea is that at the time step 0, you're having perhaps someone speaking at the front of the room here or a loudspeaker, and then over time the waves will propagate and bounce off over the different surfaces depending on the material that you have, depending on whether the surface is hollow or not, whether there's a bench in front, and so on. And we want to simulate that. And we can do it with our system where we encode this application with these high-level abstractions that I've presented, just to show you that although they are simple, they're able to express a very complex application. And then what we do, we run it on a GPU and we compare that to a reference implementation written by a human. And what we see here, this is a measure of throughput. Higher is better. It's how many giga elements in the simulation we can produce per second. We match fairly well what the human can do. And if we look at other applications, I won't go into the detail of what they are, all of them, but for instance, hotspot 3 is actually an interesting one. This is actually how I believe it is a simulation of how heat dissipates in a chip, okay? Which is, again, you can think of it as a very similar type of application, right? So the wave being the sound, you having actually a heat dissipating. Okay, and the bottom line is the version we produce, which is the first bar in the pair, is always better than what the human can write, because we have this tool that can automatically explore hundreds of different variations and find the best one for this architecture. So I'm coming to the end of my talk, and that's good because we just have a couple of minutes left. So the next thing is, up until now, we have been focusing on targeting this GPU. Okay, the code I've produced here, perhaps I should have highlighted that. We run it on a GPU. This is an AMD GPU, but results are very similar to NVIDIA. And now the question is, okay, these GPUs are there, they exist, great. If we can exploit it, that's great. But what if we could design the perfect accelerators for your problem? So instead of using one that exists, what if we could design one from scratch? So designing accelerators is a hard task. It takes many years of engineering time, okay? So what we would like to do now is take the compiler to the next level and use the compiler to generate hardware. So the main idea is to use exactly the same process. We're gonna be starting with a high-level representation of our program on the left-hand side, apply some rewrite to transform it step by step, and then in the end have a very simple process to convert this program into actual hardware. Okay? And that's an example here of some hardware that we produce for matrix multiplication actually. And as you can see here, we're having some block RAM buffers. So this is a version that actually going to be reading perhaps a portion of matrix A, a portion of matrix B, store it in some block RAM, then do some matrix multiplication locally with an accumulation variable in the middle, and then write back the result. Okay? And if we can do that efficiently, then we will manage to automate the design of accelerators, which means that tomorrow when you have a new problem coming up, you can put it in the compiler, ask it to generate an accelerator for you, and then if the accelerator you want to generate can be run on an FPGA, for instance, which is a reconfigurable fabric, then you can just get your fast accelerator in a couple of hours. Okay, so there is a lot going on in my research team. So this is on the left, the people that are currently in my team. The 4 first one are actually still in Edinburgh. They're finishing the PhD, and I have 4 new students that joined McGill this year. I have many positions available. You could come to do a summer internship, honor project, master degree, or PhD degree in the group if you are interested. Multiple topics of interest, so compilation to accelerators, hardware synthesis, machine learning applied to compilers. So again, as I explained, the compilers have a lot of choices to be made. Right now, we have some very simple heuristic, but nothing would prevent us from actually taking machine learning algorithm to tune compilers for the purpose of tuning machine learning algorithms, okay? So it goes all full circular and meta. Other research of interest will include differentiable programming and how we could also generate an accelerator automatically for them. And if you're interested more to know about compilers, I run actually the COMP520 compiler course in the CS department, and it's gonna be running in the winter 2021 semester. There are some prerequisites if you want to take the course. However, if you are not sure, if you don't have the prerequisite, in the School of CS, we don't actually enforce these. So please come talk to me if you're interested to take a compiler course next semester. I think it's a great way to tie up together everything you've learned so far if you're on a computing engineering degree or software engineering degree. If you have a good understanding of how an architecture works, assembly, you have an understanding of how to program, but you want to know what's the missing link in between, this is the compiler course that will fill the gap. Okay, and with this, I will stop here, I guess, and be ready to take questions.
Thank you very much, Prof. Dubak. It was very, very interesting to see what is going on under the hood and the new universal approach that you are based on functional programming. So are there any questions on the chat to muting yourself?
Yeah, hi. I have a question. So you mentioned we generate lots of compilation outputs and then we compare them. On what basis do we compare them? Like how do we measure or calculate? Is it done on hardware or is there a different method to do so?
Yeah, we do it on hardware. So we can take any performance metric you may be interested in. So if we're targeting a GPU, for instance, you're probably interested in time spent computing. So what we do, we generate these versions and we run them on the GPU. And we have some smart way to discard the one that are very slow. So if we notice that you start running with a small input size, if it's already taking too long with a tiny matrix, we don't bother even increasing the input sizes. And yeah. Another thing, if you're targeting FPGAs and you want to generate different hardware and evaluate them, the metric you might be interested in might be throughput, might be clock frequency, might be area, power consumption. You basically pick your metric. The compiler is, the system we develop in the compiler is agnostic to the metric you want to tune for. Hope that makes sense.
Yeah, it does. Thank you.
Mm-hmm. Okay, so I have a question in the chat. Someone is asking, as an undergraduate summer intern, what would be expected to do on a general day? And is there a link where we could learn more about your research or apply for the positions? Yes, so I will answer the last question first. If you want to know more about my research, I have on the first page here, cdubac.bitbucket.io. So that's where you should go and you can find more information. And if you want to know what the undergrad summer intern can do, so I had one this summer. He was a CS student. So obviously, depending on if you're an ECE student or CS student, so we'll have different projects. But he did, for instance, implement a basic C code generator in our. He extended our existing compiler to target a slightly different architecture that we have. So we give him a project, and it's surrounded by my PhD students and master students to help out with the technical issues, and the bulk of the work in a summer internship would be programming with the compiler most likely and extending the compilers in some ways. Okay. You're welcome. Any other questions? So someone is asking, is the accelerator or hardware design specific to a certain application? That's a very interesting question. So yes and no, we can choose. So the easiest thing to do is to have one application and just a single one, and then say, okay, I have this, I don't know, convolution kernel I want to accelerate or fast Fourier transform. Let's just design the accelerator for that and find the best accelerator. But sometimes you may have a bigger application that requires other kernels, other form of computation. So one thing that I'm also interested in investigating, and some of my students are interested to look at that, is what if you have a set of applications? What if I tell you there are these 10 kernels, these 10 computational kernels that are very important to me? Could you create one accelerator that is good on average for the 10? So that could also be done. And one way to do that could be either to say, well, what about we create one accelerator for each and we try to put them all on the same chip? Or we can start to say, I see these two different benchmarks share similarities. What about we make the accelerator a little bit programmable? Perhaps we reintroduce the concept of an instruction set, but a very limited one, okay? So there is a lot of flexibility here when you have a compiler of what you want to do. So I hope that answers your question, David. And there is another question. So let me read and parse the question. So hardware solutions require a lot of time and also hardware to debug. Do you think that this tech can be feasible to the general public? Any particular challenges you are currently tackling? Yes, so this is precisely why we want to use a compiler. because we want to automate the process. For anybody that has coded in VHDL or Verilog, you know the pain that it is to debug your design, okay? Everything might work well in a simulator, you put it on the FPGA, nothing works, like everything is broken, the timings are wrong, and so on, and you have horrible bugs. And then you go to ASIC, and you get the chip back, and it's even worse. So this is why I believe that we should stop programming, you know, at the very low level, or at least try to make it so that very few people touch the low level, and try to raise this programming abstraction so that it's much easier for people to program. And if you think of democratizing access to hardware like FPGAs, actually this is already in the process. If you look at all the main cloud provider like Google, Facebook, and so on, Amazon, you can now go there and actually rent an FPGA if you want to, okay? If you have an application you want to accelerate on the cloud that requires an FPGA. So I think this is the direction we're going to. Because it is hard to debug hardware, let's try to generate it automatically. Yeah. And I have to say that if you have a bug in your compiler, it's another level of difficulty to debug it, right? Because then the compiler has a bug, it produces wrong code, and then you have to figure out, okay, what's wrong with the code to be able to figure out what's wrong with the compiler. So actually working with compilers is hard, I won't hide that. But once the compiler is working, it's easy for everyone else. Okay, is there any more questions? So thank you very much for all your questions.
So indeed, an extra layer of difficulty when one is working on compiling tools. So thank you very much, Prof. Dubac. So of course, the students have your website address, so they can check it out. And also, if you're interested in compiling, and also perhaps get the basic notions of Prof. Dubac research. Come 520 next semester. And good thing that I should mention now, it's computer engineering and software engineering student can take it as a technical complementary. So so you can contact Prof. Dubac if you're interested.
And once again, the prerequisites are not enforced in CS. So if you're wondering about that, just contact me and we can sort it out. Okay. So thanks a lot, Ken, for organizing all this. This was great.
Thank you, Prof. Dubac. I'm glad you enjoyed the presenting your research, and thank you to all of you who joined us.